Record. Okay, I just started the record button. We still have a minute.
Maybe I can go ahead and share the slide.
Yeah, you can try if the slide
Already,
is fine to you.
you're going to see my screen, right?
Yeah, I just see your screen.
Yeah, sure.
Okay.
Uh,
Will this be your job talk?
uh, I would say like a part of it because I have some other components that
Uh-huh.
I think for the sake of the alignment of the class, I will just talk about the healthcare aspects.
Uh-huh. Nice.
But of course, there are some other aspects, as you know, like in like foundational or theoretical RL and
Mm.
AI work, and also some work in the robotics. I'll be like very briefly talk about that, but mostly I'll be focusing on the specifics of the healthcare aspects of it.
Uh-huh. Nice. Yeah, I think this year healthcare air for healthcare is a big shot.
Yeah.
Yeah, I think I will briefly introduce your background and then after that you can get started. So, hello everyone. Thank you for taking this lecture. Today, I invited my PhD friend, Masroor, to present his research on AI for healthcare. So he's a successful PhD, and we are actually, when we are the same, under the same advisor, Dr. Yishang Xue, and he currently is a postdoc at Purdue University Engineering Department. So he moving from computer science and to engineering. Now he is on the job market. He's also get several funding because of his superior research. Today we are very honored to invite Masudou to presenting his research on AI for high-stake environment. Thank you.
Yeah. Thank you, Nan, for the nice introduction.
Mhm.
Um, I cannot see the whole class, so hopefully
Uh,
the class can see me and my slides. So
yeah,
yeah,
the laptop
yeah,
is
that's
only here.
yeah, that's fine. Yeah, so I know they're there. Okay. Yeah. So yeah. So today I'll be talking about my work on AI in AI for high-stake environments, which includes healthcare. Um, and so this would be more of a, I was like, feel free to ask any question at any point. I'll try to answer them. Also, I hope we'll have some time at the end of the talk for the question too. So feel free to ask any question if you feel at any point of time. Yeah, so let's get started. Yeah, as Nan introduced, I'm Masjidur Rahman. My research focus on the central question of how we can build AI that learn, reason, and act safely when the world is unpredictable. Right? The question connects everything I do from reinforcement learning to reasoning and robotics with the goal of creating adaptive and trustworthy autonomy. To understand where my works fit, let's start with the larger context of how AI has evolved over the time. Over the last decade, AI has achieved remarkable success mastering games, manipulating complex objects, generating language, and even assisting with design and discovery. These advances have been fueled by mostly, I would say, like data abundance and massive compute power. But in many critical settings, in this case, we'll be talking about the healthcare, thus those conditions simply don't exist, meaning we don't have like large scale data, and probably we don't have the large compute in the remote settings. So think about the scenario, how those AI system can be used in the problem in mostly characterized by the hostile environments. In this case, it can be a disaster area where you don't have the network connection, or it can be wildfires, like you don't have access to any sort of devices or any tools or compute or any technological aspect that's not available. And even in rural settings where you don't have the proper internet connection to even like access ChatGPT there, for example, right? So now the question is, are this system that is we are seeing the success in AI is ready for those settings? That exactly what I am envisioned to do and to analyze to what extent we can use the success of current AI to enable tools in those settings. Uh, so why this is an important problem? I think to this class already knows that, okay, we have the AI that can help in many aspects of scientific discovery. And of course, healthcare is a major sector that we should be focusing on. And, and these are very challenging settings that is different than the traditional settings that we used to do AI, right? So we don't have like lots of data. Uh, like we don't have data that simulate very critical scenario in disaster area, in emergency medicine, and even in robotic surgery, and even in space exploration. So the problem is that, first of all, we don't have enough data, and then the decision is very important, meaning it's a decision between maybe like the survival of a patient or not, and any kind of so that's why it's called like very high stake, meaning we need to be very robust and very accurate in terms of whatever we do with the AI. But the good thing is that it if we can build some useful AI tools for this domain, so that would be really helpful because these are the domains that we really want our AI system to work. Of course, it helps us in like writing our maybe papers or writing our like report, but we would like to have that the same AI system to help us in disaster area where even the experts cannot go, or in a many aspects of healthcare where we really are lacking in many aspects. So the irony is that these are the environment I would say like we need most AI, yet they're the one the AI fails the most. So let's see why that is the case and why this problem is difficult. Um, as I mentioned, the current AI system are very good at where we have control settings and lots of data with proper annotation. So the good thing is that now we have tool set that we can use to train really a very good system that is useful in that context. But when we talk about high stake settings, the one that I give some examples, so these things simply doesn't hold. From a theoretical point of view, we can consider that there will be a distribution shift in the data, meaning the data that you are training is different from the data you will be evaluating or deploying your system in real world. So that's a very fundamental challenge of the AI that we are using right now. Like we have this training set that we trained some AI system with the machine learning algorithms, and then we try to generalize that to some settings. Of course, the underlying assumption is that it has to be some form of IID, but in real settings, whether that holds or what extent that holds. So that's really a major challenge in using the current AI system in the settings that is very high stake and uh, and uh, and the domain specifics, especially in the healthcare. So my research vision is to develop AI that adapts and endure in this real world system that learn efficiently, faster, and also the region transparently, which is very important in the healthcare domain that I'll be talking about more. And also we need the AI system that acts safely because this system sometimes work with a human companion where the safety is very important. So this vision builds on three interconnected pillars, uh, starting from learning, developing algorithms that generalize to across environments and in the condition where the data is limited. Uh, yeah, so to give you like very brief summary of what I typically do in my research, starting from the learning aspects, I work extensively on reinforcement learning, and I also work how to connect with a new foundation model like visual language model or large language model. Include that to improve the generalization aspects of reinforcement learning, and also the domain of healthcare. In this case, I'm particularly focusing on the burn care, where how we can use this visual language model reasoning to improve the aspects of the burn care. And also the robotic surgery, which is how we can use this AI system to build a autonomous robotic surgical system. That is also another aspect I'm very interested and actively working on. So for this class, I'll be heavily focused on this reasoning aspect, like visual language reasoning for the burn care, which is talking about in a broader angle of how we can use AI in healthcare, where we don't have enough data with the current visual language system. Um, yeah, so this would be going forward our method or the things that I will be discussing is relevant to that. Is mostly on the case of how we can use this visual language reasoning for the burn diagnosis. So before moving forward to that, is there any question from the class at this point?
Yeah, we are good.
All right. Yeah, let's go into the this task. Okay, so why the burn care is important and how that event fits into the problem that I described as austere settings. So first of all, this is a very important problem in terms of if you see the number, like the burn injuries affect 1.5 million people annually, only in US. And also the burn care is very, the standard settings is subjective and sometimes inconsistent. And the standard practice is that if you see someone get burned and goes to the hospital or burn center, and then the most that the standard practice is to use the visual inspection. They sees the burn in your some places, and then they try to assess what is the severity of the burn. By severity meaning whether it's first degree burn, second degree burn, or a third degree burn. So depending on this severity, the treatment plan can change. And another aspect which is very important is that the first few hours after the burn is a very, very important time to make any decision. So the faster that the doctors can make an accurate decision, so the treatment plan can change and it can vary a lot based on how quickly the patient can recover or even can survive. So this is a very, very timely problem. That means you have to decide as soon as possible what to do with the patient, right? And even the current standard practice, which is 70% accurate in a literature that we can see that, which is not very good because if you just look at with our eyes on the burn, and that is really not possible to evaluate to what extent that this burn wound is severe or not, right? So we'll see in details why that is the case. And, and in the recent time, there is this new research in the burn area where they talk about using the ultrasound imaging. So, so this is not a standard practice, first of all, to use ultrasound. But in my research, I have shown that if we use ultrasound, then there is this certain benefit, and we can have like far more accurate prediction with a very faster turnaround. So I'll be discussing more on that. But the overall goal for this project is, can we leverage the AI for accurate, interpretable, and efficient burn diagnosis from medical imaging? And if we can, then how we can use that to actually change our standard practice from visual inspection to this AI-based system. So in order to do that, first, we need to see what is this data set is about, right? So first we developed this, one of the first data set that used ultrasound with the burn and also with the AI system that incorporated. So we have this ambush burn data set, which consists of 29 burn patients that was collected here in the Indiana. And we also have the data for the pigs, which we call it like porcine pig model, meaning they're not the human burn, but they're on the pigs. And that's how we can have some control experiments on that. And this dataset also contained this two type of ultrasound modality. One is called B mode. We'll go a bit details on that because that is very important to understand the method and also how we can possibly use this in a different context. Right? So for the B mode, that give us the structural imaging, and the tissue Doppler imaging is give us the blood flow on the burn area. And this data also was labeled with a different degree of the burn, meaning it's first degree burn, second degree burn, and also inside the second degree burn, there are two types. One is second degree superficial, second degree deep, and also third degree burn. So these are very finer details that we need to know in order for us to decide a treatment plan, meaning whether this wound or this patient need a surgical intervention or other treatment can be enough in this context. So we have this annotation from the experts. So we have collaboration with the burn center. We have collaboration with the burn surgeon. So they are all part of this project that give us this annotation. And also the ultimate truth, what is the burn severity is the histology data, which is a biopsy. And we also have biopsy data for some patients that we evaluated on our AI system, how good our AI system can predict the burn severity and different aspects of it. Of course, what we do first, once we get these things, we ask ChatGPT to see if it understands whether we can use that data to understand, okay, what is the severity of the burn? So it turns out that, of course, ChatGPT has limited knowledge about this data because, as I mentioned, that this is the very first time we are curating this data for the burn to analyze how we can use the medical imaging for the burn severity understanding. And of course, the OpenAI doesn't have access to that yet because we only own the data, right? So So that's very important. So now that if you want to use ChatGPT in any way, so how we can use that? Like, is there any way to use that without even like training a GPT model like that? So this aspect is very important and very common if you see. In many domains, we don't have enough data. Of course, we don't have enough data to train a large model like GPT. And even in medical domain, that is even more challenging because there's lots of anonymity aspects, like proprietary aspects, lots of aspects that prevent us to curate lots of data, right? Like you cannot just like burn like a lot of people to get more data, right? That's not feasible. So even in a some burn center, so just to give a context, so this 29 patients data that we collected, it's a huge efforts from a collaboration with the burn center, medical hospitals, and also with the universities, lots of protocol, and finally we get to collect this 29 patient data with a few years of time. It's very challenging to get lots of data. And if we say, can you give me like millions of data so that I can train a GPT model? So that's simply not feasible, right? So what's the gain that we can use? So how we can still use this advantage of these current techniques to actually gain more out of it, right? So to understand the problem more details, then I'll go a bit more details on why this is challenging and why maybe the ultrasound is a good modality. So before going that, is there any questions so far that we can address now?
I think we're all good.
All right, perfect. Yeah. So now to see, just to set the problem here. So what is the problem that we are dealing with? That we have a burn wound, right? So just for the convenience, I blurred the image. I think I blurred enough to make it like comfortable for everybody. Uh, so this is the real burn patient image, and then in order to determine what is the burn severity, meaning whether this wound require a surgical intervention, like going to the OR and do the surgery, or maybe some general medication is enough to actually get to get this treated, right? So why this is difficult? Because in our skin, right, we have several layers. Like we cannot see from outside, but let's consider. Let me see if I can put the mouse. Yeah. Can you see my mouse?
I don't think so.
Uh,
Yeah, this is my mouse.
right. So yeah, I need to figure that out. So why that is the case, but all right. So let's see. You can see the ultrasound image, the markers like epidermis, dermis, right? So so this ultrasound image corresponds to the skin layer, meaning at the very top we have this epidermis. So this is actually very thin. We have this epidermis, and after that we have the dermis. We have hypodermis, fascia, and then muscle. So it's a very thin layer. And the very intuitive way to understand what is the severity of the burn is that you look at the top layer, and for somehow, if you see that that layer is damaged, so then that maybe it's okay. But if you see the hypodermis, which is the lower layer, which is damaged, then that's indication of a very severe burn, meaning you need a surgical intervention to actually treat this burn wound. So that's kind of very intuitive way. But when you see with the eyes on the left side figure with the digital photograph, right? So you cannot possibly see what is underneath your skin or different layer. So this is simply not feasible to understand from the visually from the left side image digital photograph to see what's going on underneath the skin, right? So that is why this is very difficult. And and we saw that around 70% accuracy that we observed in the literature that we see because of this difficulty, because this is very, very difficult to understand what's going on underneath the burn skin, even not looking at it, right? So this is one problem that makes this problem very difficult. But if we have the ultrasound data, we can see on the right top side, we have two images. One is a black and white, and another one is a color image. So the left side black image is called B mode. So intuitively, it will give you the structure of the layer of your skin or this patient's skin. So there is certain pattern. I'm not going to like very details, but if you see like some line like this, so that's some pattern that you can understand whether some part of the layer is broken or not, or is damaged or not. And in the TDI, which is the tissue Doppler imaging, so that captures what is the blood flow intuitively, like what is the blood flow in those areas of the skin layer. It looks as a cell level, but it can give you this color, and this coloring has meaning, which that only the expert knows, but maybe the ChatGPT doesn't know yet, right? So that's the tricks here. So our expert knows what this ultrasound image means, how to read the ultrasound, right? So they have a hypothesis. What is that? They said its color pattern means something. Meaning, if you see you can see like red and the green and the blue color pattern, right? So if you see like the blue is most likely to be some scenario where you don't have a blood flow, meaning those area of the layer is got burned, right? The dead cell, so there is no blood flow in those cells, so it's blue, right? And if you see the other color, green or red, it's most likely there's some other things going on, but there's not really a case of like not blood flow. So this is some kind of hypothesis. This is not a ground truth. This is very important. So this is some kind of hypothesis that our expert, the burn surgeon, that they provide that, look, this is ultrasound that we got, and then we have this different color pattern. And if you see this continuation of the blue color, even in the lower layer, for example, the hypodermis, then it is most likely a severe burn. But if you don't see that, then this is most likely a not severe burn, right? So these are the hypotheses that the expert can provide. So now we can change the problem. Like instead of asking the ChatGPT to understand, or rather, like I would say, like any GPT type model, any LLM model, like it can be Gemini, it can be like Llama, it can be Queen, it can be any other model. Like as long as it takes image as input, when it takes image as input, we call it like vision, like visual language model, meaning it can also analyze the image and text together, right? So instead of giving this image to GPT and say, what is the burn severity, we can ask it to, to understand this pattern. Like, can you see the continuation of the blue color in the lower part of the image? So this kind of very useful way to understand the pattern. And in any sort of reasonable AI model would be able to give you a correct answer, right? So yeah, I can see the continuation of the blue pattern, that part of the image. So this is sort of so the problem become from burn diagnosis to a pattern matching, and this pattern is given by expert, which we call expert hypothesis, right? And if we can do that based on this hypothesis, then we can use the existing AI model, like GPT, Gemini. We can use this model to actually make a good prediction because now the problem is much more easier compared to what it was before. So with that, we propose a framework to actually do that in a more formal way. We can define that as this framework of Coder, and I'll be spending quite some time on this just to give of why, how we actually build this system. Okay, and feel free to ask any question if you have. Um, and I would just, before we start to this particular case, I would say that this type of framework can be potentially used in many other settings, even the setting that you are working on, right? Maybe it's a different domain. But the idea is that, okay, you have the problem, then you convert it to some problem that in a pattern matching, and you know how to do those, understanding those patterns, then how you can use this large language model to come up with a solution for your problem, right? If you use that in your research or in your problem, you can see that this is also not very reliable. Meaning, as we mentioned in the very beginning, it's a very high stake task. And if you ask the model to, hey, what is the severity of the burn based on this hypothesis, for example? And then if it sees like different answer at different times, so that is not reliable. Like you said, okay, do the surgery. Okay, not do the surgery. Wait, not now surgery. So this is not like fast or the solution that maybe it will work sometimes, maybe it will not. But how we can make sure that it perform consistently good, right? So that's why this framework, where instead of giving the entire problem, we have this pipeline. In the first, we have the problem specification, meaning what is the problem that we are targeting? In this case, the burn depth prediction. And we are saying we are giving this B mode ultrasound and the TDI imaging. So based on this information, we ask the LLM. In this case, we use the GPT 4o. So we have the detailed structure in this paper if you are interested. So first, so the approach is that how we can come up with a hypothesis, meaning what to look for. Okay, so we give this problem specification and um, ask this kind of question. So based on this specification, what things I should be looking for in this ultrasound image? And in order to do that, it can provide this logical sequence. Okay, if you see the dominant blue pattern, then it most likely a third degree burn. If you see a like red-green mix, it's not like the third degree burn. So the model can give you this lot of information. But end of the day, the output of this LLM or VLM is the text description, right? It will always give you the text description. That's why it's a large language model, meaning it will always talk with you in terms of the language. To be more specific, like natural language or English language in this context. But we also need to know, like, as this is a sequence, like, what is the hypothesis? The sequence of steps that you need to perform. So we need to see whether those steps are consistent. So that's why we need to know what is the, uh, like, how we can make sure that the output from this model is consistent. So that is one challenge that we found that it can give you different, very complex analysis, very long text, but different hypotheses, like how we can make sure that they're consistent. So we use these tricks of converting that text. Like first, instead of asking this, give us a raw image, like a raw text description of how to come up with the hypothesis, we ask, okay, you give the hypothesis, like in the first block, in the English language text, and you also give a corresponding first order logic, meaning there is a way to convert this natural language text into some form of first order logic formula. And this is also done by the same language model. You can even do better over there, but for our task, that was enough, it seems. So you ask both the textual description and their corresponding first order logic. And then, so once you get the first order logic, so that is a way, like systematic way to evaluate whether those set of formulas satisfied or not, right? So we have the SAT solver, SMT solver. So we can use the sort of the like off the shelf SAT solver to evaluate whether those different first order logic formula make sense. Meaning, if we see any inconsistencies in any part, then that means most likely that hypothesis that generated by this language model is not complete, or it is not consistent. So that's where we can go back and give this feedback loop and give it to the, the LLM again and ask it to define its uh, generation of the hypothesis. So this is kind of iterative process and a loop. So as long as we give this inconsistent formula or FOL, like first order logic formula, then we keep iterating this loop until we get all consistent formula. So at that point, we take that textual description, meaning the assumption is that when we get the textual description, then we have this the correct consistent hypothesis. So that is what propagated to part C, bottom right, you can see. We get this information of intuitively, we can say this is kind of a documents that you can use to see what is the how to read that ultrasound image. Even if you see, like, we don't use in this paper, we don't use any kind of even expert insight. So we have some other papers that we use directly from expert, but for this task, we can come up with a way to automatically generate this hypothesis itself. So that means like you can use this method potentially in any other problem that you're interested in, right? So now that we have this hypothesis generated, which is intuitively saying how to read the ultrasound image, and you can use that, any favorite VLM model to generate this prediction. So that's kind of the core of these methods. Um, so some details that we used. In this case, we used the G3 as a SMT solver, and so these steps I already described, but this is one example how those logics looks like. You can see that it can be as we talked about, like the dominant blue pattern in the image is most likely to a third degree burn if it's in a lower like a deeper layer, right? So that's a like dominant of blue, and if it's like a layer is like deep, right? So that's most likely a full thickness burn. So this is the kind of one example that you can see in the logic, first of the logic formula. Um, so any questions so far?
I think we're all good.
Great. Yeah, now we'll see like how good this method work in practice, or can we just use it as it is and pretend that it work? So in order to do that, we use this task, and now that we have this data set with the ultrasound and also the corresponding the wound annotation, so we can evaluate how good this system is, right? But we use some techniques in this case, as I mentioned that I call it like reasoning. So there are several ways to do the reasoning. Maybe this class may have some familiarity with that, but I'll just briefly describe what do I mean by reasoning in this case. Like if you ask, let's consider this, think of chain of thought, right? So, so in a settings of this prompting, you can ask the model, in this case, let's consider ChatGPT, you ask some question and then it will give you some answer. So there might be some internal reasoning and things going on, but that's really we don't know. And if we then say, okay, instead of doing that, if you give some examples of the problem that you already solved or you have some examples, then if you give that and ask the question. So instead of asking just a direct question, you provide some examples how to solve some similar problems. And it turns out if you can do that, then there is some internal reasoning that you can trigger for this model, and then it will give you a better results for the problem maybe you are interested in. So that's one way of introducing this reasoning. And of course, there are some models trained, fine-tuned to do that reasoning explicitly. Like if you go to the OpenAI or Gemini, they have a version of the model that explicitly do this reasoning. Even if you heard about this DeepSeek R1 and this model, so they are explicitly trained on using some form of RL to improve on this reasoning aspects. But this really starts from this chain of thought when people started using these examples in the prompt, and it turns out that can do a better reasoning. So in order for us to make it to work in this problem, which has like very, very limited data, so we had to resort to these different techniques that we use, and that really makes the overall performance pretty good. So one of them is, first of all, we generated the hypothesis and we just use the hypothesis as our prompt, and then we ask um, what is the burn depth accuracy, right? Based on only the hypothesis, this is one settings. And then we also use the hypothesis and chain of thought, meaning we have some data that we annotated based on this ultrasound and those hypotheses by expert, right? So we use those examples as a sort of a reasoning step, meaning as a form of chain of thought. And then, of course, if you still do that, if you ever play with the GPT model, right, or ChatGPT or Gemini, so you can see like not you can see like different time you ask some question, it will give a slightly different answer, right? But if it's like very obvious question, maybe it will do correct every time. But if it's somewhat sort of a thinking question that you need to do some thinking, then you will notice that it will give you some slightly different results, and that can be problematic, right? Um, and there's valid reason why this is doing it. Like if you go uh, very internal of how these texts are generated. So there is this probabilistic approach, right? We have this. So in a simple term, we can say this is all this language model is doing is an X token prediction, right? I think we had this again and again. So what does an X token prediction actually means? So you have this sequence of uh, token already generated, then you want to ask what's the next probable token, right? Most likely token. So that's the probability, meaning the model is sampling from a probability distribution. So that means that it's not 100% guarantee that the correct token will always appear. So there's some probabilistic things going on under the hood. So that's make these outputs different every time. And so that's really a good thing or bad thing. Because the problem that we are talking about, we have to be very, very consistent. Like we cannot say like now we do surgery, and after the surgery we can say okay now we don't do surgery, right? So this is very high stake decision. So we have to be very robust in that sense. So another way of looking into the problem that okay now that we have this different approach, so we can use this method called self consistency, right? So you see, there's a specific paper that do with it, but in a very intuitively, we can say instead of running the model once, let's run the model some odd number of times. For example, if it's some binary decision, then you can take the majority of the vote and you can decide. So that is a way to make it robust. Like instead of just running one, like run several times and take the best. Like most voted scenario. And there are many ways of doing it. Like I think if you're interested in that, you should read like the chain of thought paper, also the self-consistency paper, which really shows or some systematic way how we can better um, make this output consistent. Even the single output is not consistent, right? So that's really the final method that we come up with, and it turns out that that works good. And for this task, we use GPT-4o model and GPT-4 Mini, O Mini, GPT-4 Turbo, and Gemini 2 and 1.5. So these are the VLM's backbone, meaning we access those through the API that is available, and we were able to generate the results. Of course, like you can use any VLM models. Later on, we have used some other updated model, like some open source model that also can do the similar task. Um, but for this experiment, we use these models, and these are considered pretty good at that time. I think there are some new models come up. Maybe you should also look at those other aspects if you're interested in running some similar experiments. Right. So here are some results. It's a dense slide. Let's look at it. The coder you can see is the framework that we proposed, and the GPT. If you see like just the GPT-4o without the coder, that's the base model. Meaning we don't give any kind of hypothesis, and we just and then we ask the question how good they are doing. So overall, this coder framework improved the performance of like consistently all those base model. And interestingly, if you can see the first second row, like the GPT-4o model performed really, really bad, right? Compared to even the improvement is really high. And at the end, we get these two kind of accuracies, which is 93%. And also, so that is kind of the binary decision making, like whether you need to do the surgery or not surgery. And the fine-grained burn depth is what is the exact depth? First degree, second degree, superficial, second degree, deep, or third degree. Like it's very final details. So the first one is the binary decision making. Second one is in this case, it was a three-way decision making. So we have seen that this method actually improved the performance quite a lot, and even sometimes the better than the standard assumption, the 70%. And now the question is why the existing GPT model perform like very, very bad, right? Because if you let's look at this example, this specific scenario that we have this GPT-4, which has the reasoning. In this case, you can say like the red mark is correspond to some inconsistent information that is extracted from the image, and the left-hand side GPT for O plus coder, we can see that it performs some form of correct mapping from this image to the hypothesis, and it were able to correctly predict this. So this is really important to see that how because this existing base model they do not have this understanding of whether you can use this imaging as for the burn. Like they have different interpretation of this image, like different interpretation of this color, which is not available. But through the hypothesis generation, you can incorporate those into the model, and then you can predict better. So in another results on the left hand side description, you can see. So there is the aspect of chain of thought. Even with the hypothesis, sometimes the model can fail. It fails to generate the proper the reasoning because without the chain of thought or some examples, it will just simply take the whole image and try to analyze it. But if you give them some examples like, okay, this is the image and this is what my expert predicted based on this, like look at the first layer. First, you identify the layer of the skin, then you go and understand the color pattern, and then you go about making the prediction. So it turns out that if you can give this additional information to the model and it perform better. The top image, the top description, you can see incorrect prediction for this task that we have seen that's got solved if we allow the model to do the chain of thought reasoning. So this is really interesting that um, you can use this chain of thought reasoning even to improve further on the performance that you care about. So, so in the bar plot that you can see, if you use just the coder in this surgery versus non-surgery classification, it got 80%. And if we add chain of thought, it got like 87%. And if you add like self-consistency, then it got like 93% accuracy. So this is really, really good according to our experts that we have burn surgeon and um, we have plastic surgeon, we have like we have experts in medical imaging. They do like the patient's surgery, like, and based on their assessment, that this is a really good numbers in terms of that. So we have some other papers already some published. Some are one of the papers that we are really focusing on is the medical aspect is right now under minor revision to Annals of Surgery, which is a very prestigious journal in this medical domain. So we are really excited about these results. Uh, okay, so in a nutshell, so this would be my final slide. In a nutshell, we'll see. Uh, let's see like how this AI method evolved and where we are compared to maybe the time that I started my PhD, right? At that point, we all talk about like deep learning, like okay. So we have this neural network, and then we have this like lots of pre-trained model like ResNet, Vision, even Vision Transformer came after that. So the first category of model, I would say like let's call it deep learning, okay, in classic settings. So what's the bottleneck here is that you need lots of data. Like think about how everything got started from ImageNet. Like it has like millions of image data, right? But the problem that we care about is always be the case that you don't have enough data, right? Limited data. So so though in many tasks, in many areas, this deep learning make a like huge stride and it perform like really good. But until now, even if you use the pre-trained model, like in this case, we tested even with the limited settings. If we fine-tune a vision transformer, how the performance as we see that it's at 65% in our case, like very limited data, right? And even if we see the recent success of a large language model and vision language model, we can see even with that, we cannot even perform good if we use as it is, meaning we just ask and expect the answer, right? For some tasks, that might be easy to get, right? Because those are very tasks that is very common. You have lots of data, and those model as it is can be very powerful. But in the domain that they don't know, and there will be always the domain that they don't know, right? So that's the problem settings that I care about, like in high stake domains, that there will be always new things come up. So, so the next comes up with the hypothesis. It turns out that if you can do the hypothesis the way that we describe one aspect of it, then we have this case where we can really perform good. And even we analyze this one aspect of the hypothesis, and then we added like more reasoning with a chain of thought, and then we see that the performance goes even better in that task. We are still evaluating in a more rigorous how that case. And in this case, the 95% accuracy that you are seeing, so this is a slightly different settings where instead of asking the LLM to generate that through the coder, so the hypothesis was given by the doctor directly, which is tends to be like a little bit more accurate. So the takeaway here is that the general purpose VLMs struggle with the specialized medical data that we can see. And but if we can make sure that we properly use it with the domain knowledge, one framework that I developed turns out to be work well in the settings, then we can make accurate and reliable clinical prediction. And also the good thing is that this model outputs in terms of the language, right? Natural language. So you can see the text. It's not just predicting some output, like and giving us some numerical values, like what's the accuracy is. It's giving a natural language description, like it's giving this step, like okay, first step I took care of that, the next step I did that. So this reasoning is very helpful for the expert. Like when like show this to our burn surgeon, they are kind of very excited because they can now read the output. Like they don't need this different plot, different uh, uh, saliency plot or other plot to make sure that how the interpretation is. But now they can look at it and they can understand what the thinking process of this model. So that turns out to be very powerful and very accepting in this community that So okay, now they see the reasoning, they may understand the problem behind the reasoning, and the system can be improved from there on. So this is very powerful that we are getting the output in the form of natural language text, and also sometimes you can enable the interaction that even make the process more smooth. So this is really powerful in that settings, and even the general purpose PLM can work. So that's another message. There is also lots of research going on to make this language model to be very specific to a domain like medical PLM or many other domain, right? So that is also very good aspects of like using this LLM aspects in those medical settings. That is also very good research. But there is also settings where you don't even have enough data to build a domain-specific PLM. So what you do in that case? So that's really where you can do a lot of things on the side of hypothesis, and you can get some good results out of it. That's all for today that I was planned to talk about, and I'd be happy to take any question if you have.
Do you guys have any questions? Feel free to ask. Yeah, go ahead. I don't know if, yeah, maybe getting closer.
Yeah, maybe Nan, you can repeat if I cannot. I can
It's
hear the
coming.
class, I
It's
think.
coming.
I was just
Yeah.
wondering how well your method stacks up time-wise with just like compared, because I'm guessing this is for to be used in like medical hospital or all that. So when things are time sensitive, how well does it actually stack up with like just a doctor diagnosing something?
Yeah, that's a very good and very profound question. So that's really what the whole motivation was, to make it quick, right? Um, so in this case, the way that our system work is like, just to give you a number, like it can predict within a minute, right? So the main bottleneck is that how we can run those big model. And this particular setting, we use the API, meaning we have the API access to these models that we tried, and they are very fast. Like you ask the query, you'll get the answer like in a seconds. And now that we need to do like this sort of like for the self consistence, like we need to ask for several times. We also have a large context due to this um, like images and this takes the hypothesis. So in general, with all of this, in the current settings, we could get the accuracy, we could get back the results by like in a minute once we have all the data. But here's the point: like in the real settings, even someone need to do the ultrasound and then put it into the system. So those are the things that in the standard medical settings, like the patient come and then some nurses do the ultrasound imaging, and everything goes to the some database system. They call it electronic medical record, right? So once it reaches to the electronic medical record, so this system can just take it from there, and within a minute it can give this evaluation, which is very fast compared to even some experts, right? So in that sense, it's feasible. But also another aspect, like, okay, now that we are assuming a scenario where we have this internet connection, we have the API, right? So in another way, like if you want to like learn a system like a GPT-4o in your own machine, so that might take a lot of time, right? In that settings, maybe we need to do this sort of this in-house evaluation of, okay, how we can make a small language model to even do the similar performance, right? So that another aspect of the research that I think is going on in the general community, how you can make a small model run fast on your like local machine, so that you don't need this API access to the model, but rather you can just do the inference on your own machine. Then you don't need the internet connection. So the current settings is very fast, but it rely on the internet connection on the API. But in the future, with the improvement of this faster model and the smaller model, we should be able to do it on the remote settings too.
Okay.
Okay.
Can I ask something
Yeah, go
else?
ahead.
Yeah, sure.
Did you have any trouble having like an imbalanced data set with number of like severe burn cases and since I'm guessing there's less severe burn cases than more, how did you guys handle that if that was an issue with your data sets?
Yeah, yeah, definitely. Yeah, given that even we have the small data, that's itself a problem, right? And now that we have this, of course, in our data set, there was um, for the human data, right? We have also peaks data that I didn't talk about, but for the human data, we have such issue like most of the patient was like no first degree burn. Like of course, like if you just burn barely, you don't go to the hospital, right? So we have this sort of in our case, it's kind of balance, you can say. Like we have this first degree burn, second degree burn, and third degree burn. Even within second degree, we have second degree deep and superficial. So what we did, we have like already we have a very limited number of data points. And in order for us to do the evaluation, we keep aside around 15 burn wound, and from the rest, like we make sure that we take at least uh, similar number from each category and do the evaluation. So the one thing is that among 23, we are using almost half of them as our training. In this case, the training is really the use as a like chain of thought examples, right? So we make sure that we pick those examples from every single uh, wound, and then we do the prediction on the rest. Like we need very limited data, like few examples, like I would say like 10 to 14 examples, and we make sure that we take uniformly from there. But in the evaluation, of course, we have this slightly different variety in the data point, and that's why we have the evaluation like per burn wound type, and also there is another evaluation whether it's a surgical case or non-surgical case, right? So that was more of a like a 50-50 type. Like it's not really sort of a balance because most of the third degree burn was for the surgical case, and the rest are non-surgical. So it's seven surgical case, and the rest are non-surgical. But that's really a challenging problem to deal with whenever you do the medical imaging. But for our case, it was selected, like the patient was selected accordingly so that we have sort of a balanced distribution. But that certainly can be a major problem. Yeah.
Thank you. Just one last question.
Okay.
Yeah, sure.
Did you also have any differences in like demographics and if like your results like let's say like you had better results or worse results with like darker or lighter skin tones? Because I know that would probably show up differently in the images, or does making the image like the TDI image kind of bypass
Mhm.
that?
Yeah. Yeah, that's for this problem. Yeah, we have some results with the digital photograph as well. Okay, with only the left hand side, and even combining the left hand side and right hand side, ultrasound and the digital photograph. So for our case, that is one of the advantages of using ultrasound. You really don't have that kind of bias if you just work on the ultrasound domain, right? So that is one of the motivation why even we started doing the ultrasound in the first place, because depending on different demographic, different skin color, the performance can really vary if you use any standard vision model on the digital photograph on the left. And also in terms of the demographic, we make sure that we got sort of a well representative data from a burn center. We collected this data over 1 year time period in a hospital here in Indianapolis, Eskenazi Hospital, burn center actually. So we have some sort of variation in their demographic. We make sure that we have that variation so that we get the data somewhat representative of whatever we see in a burn center in a year. But that being said, this is somewhat also limiting factor that we have this data from one burn center. meaning the demographic is most likely some people from Indiana, right? And so that is kind of a case, okay, maybe in the future we should be able also be able to see from other burn center that I'm currently in collaboration with the two more burn center. One is in Pittsburgh, another one is Colorado. So we are trying to expand this to different demographic areas to see how that performance hold or can we use this across different centers. But in our case, we didn't see that much of a variation in terms of the demographic information because we really did not look at it separately as we are mostly work on the ultrasound domain. But that's a things that should be looked at in more thoroughly. Yeah.
Okay, thank you.
Thank you.
Thank you.
Any other questions? Okay. Yeah, it seems there are not much other questions.
Mhm.
I do have one question.
Yeah,
So,
sure.
so there is one time that you use those logical solver, and you also mentioned there are chain of thought. Are you doing like textual description based chain of thought, or are you doing like your own version, which is like logical based chain of thought?
Yeah, right. Yeah, so we are doing the textual chain of thought.
Uh-huh.
So in this framework, we only use the logical form is to come up with the hypothesis,
Okay.
right? We only do that check during the hypothesis generation.
Uh-huh.
And if you think the hypothesis is generated once per problem in a, in a in a way, and once you have the hypothesis, then you can use that for many samples to do the prediction. And in that case, we really care about the textual description, not the first order logic.
I see. So, the reason that you using those logical representation for your hypothesis is that because it's easier for you to describe, or is it more precise?
So the first order logic, first of all, we are doing it because we can solve it. So
Uh-huh.
we have a way to check the consistency.
Uh-huh.
And
Okay.
if we have a way to check the consistent like that accurately with just text only, maybe we should use that, right? But now that we know a solver that can at least do some form of checking of this consistency and that is accurate. So that's why we are using that logic. But if you have a different logic form that maybe represent your hypothesis better, and if you have some solver that even give you the better consistency check, so maybe that can be also be used here. But we use it because this is kind of a very common approach, and it turns out that like only that measure was sort of good enough for our case.
Mm-hmm. I see. Yeah, thank you for explanation. Also, I think do you have any follow-up questions?
I do have a question.
Sorry, the speaker is low.
Yeah, that's fine. It's not like related, but I just want to ask like,
Mhm.
how do you see AI in this areas in like 5 or 10 years? What do you see
Mhm.
in the advancements?
Yeah, yeah, that's really interesting philosophical question in a sense. Mm. So with the current domain that I'm thinking, right? In this, let's consider the burn area, right? We really got a good solution, I would say. So my take is that with the current AI in the healthcare domain, you can do quite a lot. You can do even quite a lot that is very valuable and powerful solution you can build for many domains, right? So so this is very promising time for the AI like this kind of LLM type of AI even in healthcare domain. I mostly focus on like surgery, meaning either it's a burn surgery or there are many other emergency medicine. So in those areas, whatever the current practice in the healthcare. So we have a really good realistic chance that we can make a lot of progress there and to really use these techniques that even we have so far to leverage on, and it can get to us like far with the next 5 years. Let's consider. But there are some aspects that I mentioned that there's also some cases where this thing doesn't hold, meaning the way that I generate the hypothesis, right? It's sort of very obvious to the doctor, experts maybe. So if you know the solution and you want to make it very faster and expedite it, the current AI system can do really good. But there are some aspects of my work as well to go about doing these robots, using the robot to do the learning and use the robot to perform this ultrasound, use the robot to perform some surgical task, right? So that's only generating a hypothesis is not enough, right? So you need to be like very robust in terms of the learning, in terms of the performing the task. So in those domain, like I'm considering a scenario where you send a robot to a disaster zone and it rescues some people, it does some treatment, right? So that kind of AI is very far still. And even I think with the current system, that may not be possible, given that our this current system depend on the case that you need lots of training data to for the training, and then during evaluation you expect the environment to be the same. So if you go like a more complex problem, like for example the robot learning and other aspects that you can really make a lot of progress, those aspects I think require a more innovation from the AI side of it. Like using the current practice might not be enough. And that is one of the aspects that I'm also working on, and I think many people are working on. I think many other people should work on. So that's kind of my answer. Like it's already useful. You can do a lot of things, but we need to go beyond that to make really useful in the settings that at least I'm care about.
That's a question.
Thank you.
Thank you. Do you follow up? Okay. Yeah, thank you, Masador. Thank you for presenting your
Yeah.
research. And also good to know that you provide the new representation, the ultrasound. Last time I see it is like only the image-based research.
Hmm.
Thank you
Yeah.
for
Yeah,
presenting.
sure.
And I think a few
Yeah.
students are excited. I believe there are some hospital here, so the student are more familiar with your research. So
Mhm.
okay,
Yeah, sure. Yeah, feel free to ask me any question, or if you are interested in any aspects of the work, I would be happy to answer. Like, I think you're not sure if you have my email, but Nan, feel free to share my email to the students if they are interested or in aspects of the paper they're interested to know. I'd be happy to like keep in touch. Sure.
yeah, I will share your information and also your talk video to the Blackboard, so the other student have an opportunity to connect you if they are interested.
Yeah, sure.
Hmm.
Sure.
Yeah, that will be the whole lecture. Uh,
Okay, yeah. Thank you everyone
uh,
for listening, and it was really great. And looking forward to the future and what you can do with this research and beyond. And
yes,
okay, thank you.
yes, and also thank you for presenting your research. It's a good
Yeah, sure.
opportunity, and also hopefully you can get a good faculty job this year.
Yeah.
Uh,
So yeah, let's hope for the best. All
uh,
right, and
okay, all right, thank you.